Look at this footage. A cowboy walks across the frame, but his coat shifts, his hat changes, and his face melts into another person. This happens because standard generative models are stateless. When a text-to-video model renders a sequence, it has no inherent memory of the frame it just created, let alone the physical geometry of the scene or the passage of time. You cannot solve this visual drift by writing a more detailed prompt. To generate a coherent cinematic scene, you have to wrap the AI in a deterministic orchestration pipeline. That is the purpose of Studio OS, a system designed to produce The Ballad of the Black Duster, a 141-shot episodic western. To make this work, the system relies on a hybrid client-cloud architecture. Locally, a Python controller on your machine handles creative direction and database state. Remotely, a Hugging Face Zero GPU cluster does the heavy lifting, processing massive diffusion model weights on demand. By decoupling the state from the compute, we can use local, logic-based algorithms to put strict constraints on remote probabilistic models. Achieving true narrative continuity is a software engineering problem. It requires building a stateful architecture around the AI. The first step in this pipeline is getting the system to understand the raw prose of a screenplay. If you pass narrative text directly to a video diffusion model, it fails. The model gets confused by dialogue and stage directions, rendering chaotic, unusable shots. The script first passes through a local Gemini flash node. Here, the LLM functions as a semantic parser to extract structured logic from the raw narrative. The node splits the data into two JSON arrays. It isolates visual parameters, appending cinematic directives like 2.39:1 aspect ratios. Simultaneously, it isolates dialogue, mapping lines to a voice roster. JC Black routes to a baritone voice ID, while Spud Higgins gets a raspy profile. This structured JSON output acts as a deterministic routing mechanism, sending exact instructions to the downstream audio and video rendering APIs. The LLM functions as a compiler, translating the messy human story into executable system commands. Routing instructions is only a partial solution. Visual diffusion models have no concept of narrative pacing. If you generate the video and the audio concurrently, the dialogue will rarely match the length of the visual clip. To fix this, Studio OS uses an audio-first backtiming matrix. The system halts the video pipeline and dispatches the voiceover payload to the text-to-speech engine first. This waveform represents the synthesized narration. The local controller measures its exact physical duration, assigning it to variable t. It then applies a formula, multiplying that time value by the target frames per second to establish a frame count for the shot. That precise mathematical frame count is fed directly into the WAN2 video node. The video model knows exactly how long the shot needs to be. It parameterizes camera movement, like this slow pan, to match the voiceover perfectly. Time goes from an unpredictable generative variable to a mathematically controlled constant. Even with perfect timing, text-to-video models suffer from severe visual drift between consecutive shots. The architectural pivot here is moving away from pure text-to-video and relying entirely on image-to-video generation to enforce continuity. This is managed by a local SQLite database, operating in write-ahead logging mode to handle concurrent operations without deadlocking. We generate high-resolution master character cards once and store them securely within this local database. The tandem continuity engine extracts the card and injects it as a latent image seed. A sliding window tracks metadata and lighting keys from the previous shot, passing it directly into the current shot's input. Finally, a 5-point truth table automatically evaluates the output, verifying the character's identity, wardrobe, and framing before it commits the asset to the disk. The visual hallucinations of a diffusion model can be anchored across multiple cuts, but only through rigorous local state tracking. In a production involving 141 individual shots, cloud compute quotas will inevitably run out. Relying exclusively on a single Hugging Face Zero GPU instance creates a point of failure that will halt the entire workflow. To prevent pipeline stalling, the local orchestrator utilizes a multi-tiered fallback cascade. This flowchart illustrates how the system handles errors. When it catches a quota limit exception on the primary GPU, it reroutes the execution to alternative API paths. For audio, if the primary text-to-speech engine fails, the payload gracefully switches from Zero GPU to Google TTS. For video, the system steps down from WAN2 to Google VO, and finally to generating free cinematic keyframes using Imagen 3. The complete loop is now resilient. LLM parsing organizes the data, backtiming synchronizes the pacing, the database forces continuity, and automated fallbacks keep generation moving. The future of AI video production does not rely on a single massive model. It relies on intelligent, local state algorithms constraining remote probabilistic engines.